लाइक करने के लिए जा रही है।
Where were you
Hello.
Where is the is it audible? Hello? Oh, it's not. Hello? Am I audible?
Yes, you are audible.
Okay, good. Yeah.
Okay, so we are going to start the session after lunch. So Dr. Purbita Jana is here. She will be talking about first order logic. So it's not related to anything related in her first talk, like she spoke about topology. So this thing is not related to topology. So this will be an extension to the propositional logic, which was there yesterday, and the talk was delivered by Professor Mohua Banerjee. So yeah, she will be speaking about first order logic. Over to you.
Okay. Thank you, Annay, for such a nice introduction and mentioning that it is not at all related with topology right now. But I can relate topology, but not totally for sure in some sense. Anyways, so this is the continuation of the idea of propositional logic, whatever covered during the lecture of Professor Mohua Banerjee. So she already mentioned to you that propositional logic is not that much expressive to talk about your most of the mathematical structures. So there you can think about first order logic in some sense, and she mentioned that why first order, you will get to introduce to that. And of course, not all mathematical structures I cannot talk about via first order logic, so I need some higher order logic in fact. But today I'm just going to concentrate on first order logic, and this course is very much needed in I think Amit's consecutive talks about syntax semantics duality. So that is why you need to understand what is syntax and semantics. You already have some idea what are the syntax and semantics in the propositional logic. So today I'm just going to talk about the first order logic. Mainly I will focus on what are the syntax and semantics for that enriched logic than propositional one. Okay, so first of all, try to understand that what we so far had the introduction about the propositional logic. There we talked about propositions, and also today Mohua mentioned that it is also known as statement logic or something like that. And that means actually you do have some propositions. So the propositions are the statements which can be either true or false, and you can verify which statements are true and false. And taking care about the valuation function, you can understand that what kind of formula, how can you just talk about the truthness of the statements and the compound statements and so on, right? So you can see that whatever kind of mathematical structures we so far talked about is about, like, say, order algebra, right? Some order structure, that is that partial ordered set, lattice. In fact, in the view of order, we already studied what is a Boolean algebra and so on. And also we studied like some of the idea of group theory during our category theory course. Like they used to took the examples from this theory and so showed that how group will form category in different ways, defining the morphisms and objects and so on. And also we talked about sets, of course, and topology also in our course. And also, I guess that we all went through about very nice structure, whatever we had from our very, early life, that is in our school life. We talked about arithmetics, right? So we do know what is arithmetic. So this kind of thing we used to talk about, like arithmetic. Okay. So we used to talk about a lot, but we never formalized them, right? Like propositional logic. We just know how to talk in this language, but the formal ideas we really don't know yet. So to be able to talk about all of these things, what I actually used to use actually. So you can see that many times whenever we are doing the arithmetics and all, or group theory or order, say, we took care about variables because we were talking about that when x equals to something or when x greater than something or something like that, right? And also we talked about functions, like in group theory, the composition was the binary operation, which is nothing but the idea of function. And also we talked about relations sometimes in order theory, right? So we talked about some kind of relations as well. And you can understand, and also we talked about some of the constants in it, like for the definition of group, we were talking about very special element of group, which was the identity with respect to the composition, right? And some people are comfortable to talk about group theory, not mentioning the identity, but they can just define it using the idea of the composition and all, defining the properties of identity, and they can pick up which element will play the role and so on. But as I am fond of algebra very much, and in universal algebra, we used to collect all the constants, all the functions, and we start talking about the structure of that algebraic structure kind of. So we need to use constants as well to be able to define my to able to talk inside those theories, right? Also, sometimes you will see that when I want to check some properties of some element, then I had to check it all for all the variables in the underlying set, right? That we also did in general. Like if I had this kind of ideas, like for all x, say x greater than 0 type of things, then if I ask that whether I can talk about whether this statement holds or not, what can you say? Oh, I should see that whether. So online people, my online participants, please, if you have any question, please unmute yourself and talk with me, okay? Otherwise, I can't understand like whether you do have a question or not. So can anyone tell me that I can talk about like what will happen for this kind of statements or something like that? And I shouldn't talk it as statement, kind of well-formed formula or something like that. I will define it formally, but I didn't do it. I'm just trying to motivate you that what I am going to do actually. So can you talk about this, like, or do I need to specify some more thing to able to talk about whether it holds or not? Yeah, in the propositional logic, we can't. That's truth. But I'm just asking that, say I know all the mathematics right now. Like I already told that we informally did lots of work in it, right? So what I need to have to be able to talk about whether that holds or not at all. It is just like for all x is greater than 0. Say I'm talking about the order, about the natural ordering, whatever meaning I do have in my mind. So to be able to give some meaning of that, like I'm not talking about this, I will make the distinction of all of these things, but let me know like whether can I talk about that things should hold, or I need to specify something to talk about that.
Universe?
Yeah, kind of place where from I can choose my x. So kind of universe, idea of universe. Or in logic, we used to call it some domain of interpretation or something like that. I will define it. Okay. So I need a set where I can verify whether all the elements sitting inside here, this property holds or not, like that, right? So then only I can talk about. So I need to specify some of the set. Now tell me, if I in particular take the set of natural numbers, does it holds?
No.
Yeah, because all the natural numbers are greater or equals to 0. Now I'm just going to take a bigger set than that. If I take reals, will it hold? No, because not all reals are greater or equals to 0, right? So that's the idea. And now, in fact, I can write down this as well. That's not a problem. Okay, so you can see that the specification of underlying set for a mathematical structure is very much needed to talk about the properties, right? About the elements of the underlying set, right? And another thing here, what we saw that I had some smaller set, I just extended it, and I see that this is no more true there. Sometimes what will, sometimes what will happen, like, is it the case? Yes. Okay. So another example I can talk about, like, think about the polynomials whose coefficients are real. Those are known as real polynomials, right? So if I am talking about the real polynomials, and I am talking about root of the polynomials, root of the real polynomials, then can anyone tell me that in which language I will be able to talk about the polynomials, like your known rings or fields, right? So say field. And I can talk about it easily. We already talked about it, right? So now I'm asking that whether root of all real polynomials will give you a real number or not. That means, is it closed under the real roots? I mean, the set of all roots of any real polynomials? No, yes. Because of what? I can pick this real polynomial and I can find that none of the real numbers will satisfy this polynomial, right? Equation. So that's how the complex number came in. Like, if I want to make it closed in some sense, under these roots, then I need to extend my field or that underlying set to the complex numbers. And then I can easily say and verify that any polynomials is, in fact, complex polynomials, if I take the coefficients from complex, then also the roots will be a complex number, nothing else. So the thing is that some of the properties I will get when I just extend my underlying set, like here the field, and that is the notion of that algebraically closed field and all. So that is the kind of motivation I wanted to talk about. And you can see that to do work on these things, like, to be able to talk about all those things, I had to take care about, give the meaning, I need to take care about the domain of discourse or universe. What I think, who mentioned, I forget. Who mentioned it from the online participants?
I mentioned.
Yeah, Sujit. So I need to specify them to have some meaning of that. And also the thing is that to enable ourselves to talk about all those things, whatever we are talking about, we need, on the top of the propositional things, I need variables, because we had only propositional variables there in propositional logic. I need to take care about variables. I need to consider constants. I need to consider functions. I need to consider relations, and so on, to be able to talk about. So now formally, I'm just going to talk about, like, what is the, let me better to go here. So what are the language? I'm just going to talk about the language for first order logic, and precisely the denotation will be FOL, that is stands for first order logic. Okay, one thing I should mention, why first order, because by now whatever I talked about, it's about the wherever I talked about this quantification so far, I can't quantify it on the elements of the domain of discourses, right? So if I do this, if I am able to apply those quantifications, sometimes there exist also we used, right? So if I quantify things over the elements of the sets, then I am in the first order logic. So, and you can understand that I talked about topology as well. Can I talk about topology with the help of only quantification on elements of sets, or do I need something more? So what is the topology about, the structure of topology? The open sets. So I need to quantify over the open sets to talk about that structure and all, right? So you can see there I need the quantification on the subsets. Also, sometimes I need to quantify over the functions, relations, and so on. So those things will be allowed in the second order logic, not in first order logic. That's why I claimed that first order logic has not that much expressive power as the higher order logic, right? So I need to extend myself. But the thing is that we need to see that whether this logic will behave well or not. That means in the sense of soundness and completeness, right? But anyways, today I'm just going to talk about first order logic. I will confine ourselves to take the quantifiers over the elements of the sets. We are not going to talk about these things. So we are unable to talk about topology right now. Anyways, so I'm just going to talk about the language of first order logic. By now you already know that Mohadi already mentioned that whenever we are going to talk about some language, starting from natural language to any language, say propositional logic language, we need to first talk about the alphabets of that language. Then I need to construct the words, and then I need to construct the sentences, and then I can start arguing, right? So that is the idea of the language of some things. And what are the language alphabets for the first order logic? What could be? I already told you that I do need at least that propositional logic things, right? And on the top of that, I'm just extending my language. So I'm just somehow trying to keep my propositional logic inside it. And we may see in some way that how we can see that inside the first order logic. Okay, so my alphabet will consist of constant symbols that we need. So countably many, possibly. And this may be sometimes empty as well. That means it may happen that my language has no constant symbols as alphabet. And also I'm just going to allow function symbols. With arity I, because you know that whenever I would like to talk about the functions, I need some arity type of notions. I hope that Amit preferred to take the arity in like as a function inside the logical language, but let me do it like this right now, and maybe you can understand that how you can just do that. So say I is the arity, so I can have countably many such function symbols I'm allowing in my alphabet, so on, where I is a natural number. Similarly, I want to confine some of the relation symbols that we used to call predicate symbol, and that also can be empty as well, possibly empty. Predicate symbols. Here also I need some arity here. Arity. Did I wrote I? So TI1, TI2, and so on, where I is from natural number. And the what else I need to in my alphabet to be able to talk about all the theories, whatever variables, yeah. So variables such as x1, x2, dot dot dot. What else? Logical connectives, because it was there in the propositional language. So this, say this and this, and what else? Quantifiers. So I can take for all there exists, or I can take one of them. I like later on I can show you that I can abbreviate one of them from the other. Like we had logical connectives in propositional logic like this and this as well, and it could be abbreviated by the help of this arrow and this knot, right? Yes, I already talked about that predicate symbols, which will play the role of relation symbols. And the thing is that why I called it predicate, like this first order logic, also known as the predicate logic. And I'm not going to in details like why predicate logic. Actually, if I go to the natural language argumentation, then it will be much more clearer. But for a brief idea, I can say that whatever I talked about in this theories, I actually talked about some of the properties of the elements, right? So properties of the elements are nothing but the relation between that that object and that property. So that's how that means I'm just studying about the properties or the predicates, right? So that is why the logic also known as predicate logic in some literature. And anyways, I'm not going inside this, like actually it comes from the word like subject and predicate, and then there are lots of things. Like if I have time, I can explain, but now I don't want to go inside this. And do I need something more, or shall I close it? Yeah. So I already told you that equality is very much needed in my structure, right? So if I want to talk about the roots of a polynomial and I want to formalize these things, I need the equality very much. And the thing is that some people used to talk about equality precisely and some people doesn't, because this is another relation, right? So, but I will prefer to take equality because some of the logics are with equality and without equality. So for that equality, I'm just going to assign one very special sign, which is equality dot. That is the symbol what I'm going to interpret as the equality in my semantics. Okay, so that I need, and of course I need to take care about this parenthesis. Why? Because I need to club the things. If there will be some confusion that what are the well-formed formulas or terms when I'll define, that parenthesis will be badly needed. And it was, of course, present in your propositional logic alphabet also. And I already told you that I need to take care about all the propositional logic fragment inside first order logic, right? And do I need anything more? If not, then I should close it, right? So that's my alphabet for my first order logic. Okay, so now let us try to talk about the structure of those theories, right? So when I was talking about that mathematical structures, you could realize that what was enough to talk about actually among those alphabets to define a structure, mathematical structure. I mean, of course, variables are needed in any language, right? No, well-formed formula I'm not talking about really. I'm asking about that to define my structure, what things are really essential, like what kind of symbols are really essentials. I'm just going to club them and I will call them in some special, by some special name. That's the idea.
Some kind of position
we need. Variable will be present anywhere, I guess. Like it is not specific, right? I'm asking about the specific for the for defining my structure. My
Quantifiers.
Yeah. Who's that?
Me, ma'am. Alia.
Yeah. Alia, do I need? Is it that quantifiers are structure depending things, or it can be present anywhere? They're the same. Alia, you get the idea what I'm trying to ask you? Is my question is clear to you?
Not exactly, ma'am. I'm just.
I'm asking actually I am not doing a very proper thing right now, but I already told you that to see the group structure, we actually many times we uttered this word that this is a group structure for the group, this is the structure for the topology and so on, right? So if I want to specify my structure for a specific theory, so what things are specific, like in this collection of alphabets? Like variables can be taken, as many variables I need to do express myself, I can take it from the set of variables. But the thing is that function symbol, for example, it is specific for a specific theory, right? Do you agree with me?
Yes, ma'am.
And what about the relation symbol? Someone told that predicates also need to be specific for a specific theory. Do you think so? You agree with that? If you are confused, you should tell. That's not a problem, actually.
Yeah, ma'am,
Only
I'm
the
not
constant.
exactly
Yeah, who's that? I can see.
I'm Devanjan. So only the constant symbols, the function symbols, and the predicate symbols are specific to the particular structure.
That is your belief, yes. What about Alia? Alia, are you confused or you are not getting the point?
No, ma'am, I got it. Ma'am, I got it.
You got it, right? Okay. So Devanjan told me that constant symbol is also this kind of like structure specific, right? So you can see that all other things I can use whenever I need in my any theory, right? So those are kind of the special kind of alphabets. So I'm just calling those things. I mean, I'm just going to take, where should I write? Okay, let me write it here. So I'm now telling that what are the logical language, because I'm defining the language, right? So some people used to call it logical language. Some people used to call it parameters. Parameters, and will be denoted by this is the collection of all constant symbols, that is set of constant symbols, set of function symbols, set of predicate symbols. Understand? So if I have a given, like if I, what can I say? If I define the alphabet, some of the alphabets are really structure specific, right? And those are the constant symbols, function symbols, and relation symbols. And if someone provide you, you can understand what structure you are trying to talk about, right? And those will be known as the logical language or parameter. Now tell me, like, what will be the logical language for, we have already studied it, the theory of order. So for order, what constant symbols I need to talk about my theory, what relations I need, and what functions I need. So what the constant symbols will, because I need to form a triple, right? A set of constant symbols. What are they? Yeah, that is empty. And what about the next one is function symbols? So
It's also empty set.
Empty set. And what about the single binary relation? So I can just pick one binary relation here, right? One of the binary relation. And I will give the meaning when I will interpret all the things. There is no meaning. I just know that the logical language for my theory of order is this, right? What about set? Or not set, but maybe group. What it will be? So what are the constants in group?
The identity element.
Identity element, because I like to take it. Okay. And what about the function symbol? What about the predicate symbol?
The function symbol is the single binary relation, which is the group operator, and the predicate symbol is again the empty set.
So one binary symbol I need to pick, right? So that's my logical language for the group. And what is the logical language for, say, arithmetic? I mean, P arithmetic, and what specific constants I need to pick, and what functions I need to pick, and what predicates I need to pick. Plus on dot means? So one binary relation, because I don't have any meaning right now.
One binary function,
two binary function symbols. Those are the function symbols right now. And do I need more, or how can I construct numbers actually? That I need to know in piano. Zero I need, and from zero I can make the successor functions. So that is a
One
unary.
unary relation.
So one unary function, right? Do I need a relation here? Of course, I need a order relation to talk about all the things, right? Like how the order are going on and so on. Okay, so do you want to make more, or I can, or you have the idea that what are the?
Can
What?
you explain group language again? What exactly is F12?
Oh yeah. Sorry. Yeah, just a moment, I'm coming. Yeah. Oh, that is 2 early. Sorry. 1, 2. I just made the change. Sorry. Yeah. Who's that?
I am Bhargav. What
Yeah,
exactly
Bhargav.
is F12 in language of group?
Yeah. What is the language or group you feel like to define my group structure? What I need, like which constant symbols I need?
Constant is fine. Identity is okay.
And then
What
I
is
need?
F12, the set of functions which you need?
No. F12 means what? What I specified for. I mean, please go to that board, please. So can you see that board? So what are the
Yes, the function symbols.
function symbols? So what kind of function symbols are present in group theory? Like to talk about the group theory.
The homomorphism.
Homomorphism. Why I need the homomorphism? This is a property of what? So I'm talking about the group theory. I'm not talking about that, like what function they can go from here. And I'm just trying to see that to define my group, what I need actually, the group structure I'm talking
Okay,
about.
okay.
So what I need actually? A composition, right?
Right. The
That
operation.
can be anything. So that is a binary function, right?
Okay.
And that binary function can be specified, I mean, symbolized by the F21, say.
Okay.
Because I don't have any meaning right now. I'm just trying to
Okay.
see what are the logical language or what are the parameters for that theory kind
Okay.
of. Understand?
Thank you.
Also, I didn't
Yeah,
talk
yeah.
about theory, but already we had in our head, it is embedded what we are working on and we are trying to formalize them, right?
Right.
I think they're still into morphisms and stuff.
I know. They cannot get out of that hangover of category theory, I guess. Anyways, so it's good that you are just trying to understand all the things and trying to connect all the things. That's very good. Okay, so is it clear? Then I'm just going to stop giving examples of logical language. Yeah.
In all of these, it's the underlying set implicit, like
No, not really. Here I am not talking about any set right now. I just talked about that. What are the logical language? Like what unary, what binary, what trinary, and what function symbols should be there, what relations should be there, and what constants should be there. Because they will give you the structure. If you remember, like when I talked about topology, I asked that what are the structure of topology? I need a structure preserving map. Those are the open sets. And also, I think you also told about like group theory, that group structure. It consists of what? The composition and of course the identity, right? So that's the thing I am talking about. I'm not giving any, because I told that I'll start to giving the meaning when I come to talk about the semantics. I'm just going to formalize all the things right now. So because you already encountered that in propositional logic, we talked about syntax and semantics, and then we just made a connection between them, right? So here we are actually in the syntax part right now. Better to write down that we are working on syntax now. And when I'll talk about semantics, I need to take help of this specific sets. What is your underlying set? What you talked in the category theory course, right? So that I need. And maybe it is confusing because I started with like whatever we know and what we want to formalize. Maybe it becomes confusing to you. But anyways, like forget about all the things and try to see that what could be the formalities to talk about the first order logic. Okay, so let us talk about only this. And now what we are trying to see that what language it is. So what I need now next, we already constructed alphabet and some special alphabets are knowing as logical language. And now I need to construct what? Terms or word of the language, right? So what are the terms? So we already have some idea of well-formed formulae, but not term, I guess, in propositional logic, right? But here I need to first make the word, and then I will talk about this word in sentence or well-formed formally, right? In some sense, but I don't need to talk about sentence because there exists some notion of sentence as well in first order logic. So I will define it very at some point, of course. So what are the terms that I need to specify? So what are the terms? I specify that I started with constant symbols, right? Any constant symbols or terms. Yeah. Can you understand like what I wrote? Like any constant symbol Ci or constant symbol Ci is a term specifically. Right? So because like with constant symbol, we are not going to talk about some argumentation or something like that. This is kind of a word, and with this word, I can construct some of the well-formed formulae later on. And what else I want to take in the terms? Any variables. Bi is a term. Okay, designate variable by xi, right? Yeah. So those are the primitive terms, and because I am not constructing them, and if I pick one function symbol, say if in or if jn, this is a function symbol, then of course, you already know that if I have n-ary functions, I need to apply it on some n number of things, right? So that is why I need not only this, but and say some t1, t2, n many, how many arities, I mean, what is the arity? I need to have that many of terms. Like if I have this, then if jn followed by this t1, t2, is a term, and last I'm just going to close it, nothing else is a term. Is that definition clear of term, like whatever I have written? Now tell me what could be the terms of the language of, I mean logical language of this specific theory order. So what could be the terms in L order? Terms are? Anything else? By the definition, no. So only variables are the terms here. So what are the terms in the group theory? Yeah, so better not to write C or better C1 or this is again C1. So C1 and what else? Variables, yeah, all the exercise, whatever I need, and two terms. So I need two terms, right? Understand? So term will looks like that in group theory. What are the terms for arithmetics?
Are you not writing parentheses after F1 to even comma t2?
No, I'm not writing down. I'm not writing down.
You know what are the arguments?
No, when I will give the meaning, I will do that. Not now. Okay, so what are the terms for arithmetic? C1, variables, and some t, right? So those are the terms. So the terms idea is clear, I hope. And now I'm just going to talk about the well-formed formulae. So you can understand, like in the propositional logic, we had some atomic formula and we had some composite formulas, right? Like in term also, we have some primitive terms and we can make terms out of this as well. So here also we do have some idea of this kind of well-formed formulae as well, which doesn't, which is not constructed but is taken as well-formed formulae. So if I have an n-ary predicate symbol and I have T1, T2, Tn, then I mean in many terms, then I will tell that this Pjn followed by T1, T2, Tn is a well-formed formulae. Similarly, second thing I'll define like this, like Ti equal Tj equal means this symbol. So I'm just uttering it equal, but it is just a symbol right now, is a well-formed formulae. And what else can be? Just look at the alphabets. So what else I will allow for my well-formed formulae, because I need to use everything, right? Parenthesis will be a well-formed formula. How?
We can use it.
Oh yeah, we can use it. Yeah, yeah. Tell me, like, what can I say? Like, I have logical connectives. So if alpha, beta are well-formed formulae, then alpha arrow beta is a well-formed formulae. And if alpha is a well-formed formulae, then not alpha is a well-formed formulae. What else I can quantify, right? So for any, like if alpha is a well-formed formulae, then I will allow that for all x alpha, where x is a variable, is a well-formed formulae. Now tell me what else I need. If I don't need any, I will just close it. Otherwise, I will include it. Do I need something more? Is there anything left from the alphabet? Not really, right? So let's do nothing. So that's the idea of the well-formed formula. Now, can you give me some example of well-formed formula in those theories, like, I mean, logical language? Just give some example in ordered theory. P1, 2, x1, x2. Yeah.
Don't write there.
Oh, okay. I'm already up. I forget. Sorry. So I'm writing down actually here maybe. So what I can write here, say you are talking about that P1, 2, T1, T2, T1, T2 or something else. I don't know. You are talking about x1, x2. Okay. x1, x2. I have it. Yeah. x1 equals to x2. For all x? x1. Okay. So can you give me one example of strings which will not be a well-formed formula? What? Why it is not? Because I need at least two terms, right, to be able to talk about it. So that is not a well-formed formula. So it is clear, right, what I am talking about, right? Okay. So now you can see that for the variables, some of the variable, like actually my variables are term, right? So variable may occur in many places. And also I use a specific type of variable here. for all x alpha. Say my alpha contains some of the variables and maybe x, y, and many. So there I can see that the variables present in alpha has some special, what can I say, like some speciality, because it is somehow, what can I say, like fall under the bound of that for all. Or if I talk about their exists, then also it will do the same, right? So how can I, like now my question is that how can I, just a moment, let me erase this first. Okay. Make the distinction between these two type of things, right? So the thing is that first of all, in terms, I only have variables and there is no, I never talked about those quantifiers, right? So I can just think about the variables, how many variables are there in the terms, like what are the variables in those terms. So if I have a given term t, say t is a term, is it visible, Amit, or I need to, okay. So let t is a term, or let t be a term, and we denote var t as the collection of all the variables in the term, right? So my terms will look like what? Either it will be a constant, or it will be a variable, or it will be a, it will be formed by the function symbols. So if in particular my t equals to c, some c1, then var t will be what? What are the variables in the constant? No variables. So that is empty, right? And if my t equals to xi, what is the variable? Itself, right? And if my t equals to, like, I should write down not this equal, that will be confusing at some point. So say fni t1 t2 tn, then what will be my var t? That equals to what? How can I specify the variables in that type of terms?
Var ti.
Yeah, var of
Union
ti.
of var ti.
Or union of variables in ti, right? And I goes from 1 to n, right? So that's the idea. Like those are the variables present in my terms, right? And terms are of the form of this type only. So similarly, I can talk about all the terms. And now I'll talk about the let alpha be an well-formed formula. So if it is a well-formed formula, then you can see that I do have two types of variables right now. One is under the scope of the quantifiers, and others are not in the scope of the quantifiers. Whatever will be under the scope, in the scope of quantifiers, I'll call them the bound variable, and whoever are not under any scope of any quantifiers, we'll call them free variable. And and you can understand that here I do have the ideas of free variables very much in. So if I want to designate that FP stands for free variables in some alpha set, then free variable of, like, what are the formulas are looks like. So this predicate symbol, n-ary predicate symbol followed by this n many terms, that equals to what? What are the free variables here? Any idea? You can understand now what are the free variables, what I talked about. If it is not clear, please ask me. What are the free variables? Free variables are what? The variables which are not, like, which are present in that formula, and not under any scope, scope of any of the quantifiers, right? Do I have any quantifiers here of this form of formulas? No. So what are the free variables then? Any variables present in that, right? Present in what? Any variables present in what? All those terms, right? So this is nothing but union of variables of Ti, I was from 1 to n. What about the second type of formula? Free variable of this kind of formula, what it is? Ti equals to Tj. That equals to what?
All the variables in Ti or Tj.
Yeah. Okay, so what are the free variables in the third kind of is what? It's alpha arrow beta, right? Similarly, I can talk about all of them. Now come to that free variable in, because this is the specific type of things, right? This kind of formula. So what are the free variables of this?
Where alpha?
What?
Variables in alpha.
Where alpha minus x.
Because x is
Because-
not free, right? It may happen that the variable set of alpha contains x. Of course, it contains x.
Okay.
So I need to discard it from the set of variables, right? Understand it? Because I do have a bound
Yes.
variable here, which is x. So this is nothing but variable present in alpha minus x, right? So that's the idea of free variables. Yeah.
When you say free variables in alpha minus x.
Oh yeah, free variables. Sorry. Yeah, I made the mistake here.
Integration also you should say.
Yeah. Yeah, because those are the formulas. No more. I'm using this, but why it is becoming so white now?
You can get new ones. You can use them.
Okay. So the thing is that if I take just a moment, variable presents in alpha minus x, does it serve the purpose to have the free variables only? Because alpha is a formula, right? So alpha in particular can be some for all x or for all y, some other beta, arrow, something else or something like that, right?
Yes.
So
So
does
should be
it
free
serve the
variables of
purpose?
alpha minus.
Yeah. So I need to collect all the free variables of alpha, and then I need to substitute x from it, right? And that is why define free variables of, could you please go to that board, Anna? Yeah. That is why we need to know what are the free variables present in alpha or beta type of formulas and not alpha type of formulas, right? Because for the what can I say, for the atomic formulas, I don't have to take care about the free variables there, because alpha in general can, whenever I call that alpha is a well-formed formula, then it may contain some of the quantified formula as well. Understand? So what are the free variable of this? Then only I can come to that actually, and then I need to talk about free variable in not alpha. So what are they? So alpha or beta will be the collection of free variable in alpha union free variable in beta, and here it is free variables in alpha, and that is actually collection of all free variables of alpha minus x. Do you agree with me or not really? All of you are agreeing with me that is it, I mean, it's correct to collect all the free variables like that?
Yes.
Fine. Okay. So I think that's it for now for the syntax part. Let's come to the semantics part. That will be more enjoyable at some point, I guess. So I think would be better. So now we are going to give some meaning, right? So to give the meaning over that, we already observed that when we are talking about these quantified things and all, we had to talk about some underlying set from which I can pick the values of x and verify it, right? Like when I was talking about that for all x greater than 0 and kind of things. So if I want to start interpreting or give the meaning of those syntactical things, then I need to take a set, what we will call domain of discourse, and then I need to assign the values to the terms in some way, and I mean not values, but I need to interpret the terms in some way, and then I have to assign values to the variables and see that what valuation function will stand for here, like in propositional logic. Like in propositional logic, what we did, we just took the, we just assigned the values for each proposition, either true or false. And then we talked about the truth table of those connectives, and we had the valuation functions, all possible valuation functions. So similarly, what can we do here? So I'm just going to talk about the interpretation now. And I guess that Amit will like to talk about L structure in case of interpretation, what I'm just going to talk about. So this L structure, so you can understand that I'm just going to interpret those, what can I say, logical languages in some sense. So an interpretation is what? Or L structure. Let me denote it by this script I. What can I say? Consists of these following things. Consists of number one, D domain of discourse. And second, I'm just going to say that for each constant symbols present in my logical language, I'm going to get one member inside this domain of discourse. That can be any set now. And what else I can do? What else I had in my logical language? Function symbols. So what is expected here? IRE function over D. That means what? That should be a function from where to where? D to the power I. That means Cartesian product of D for I times to D, right? And what else I do have? Predicates. So how can I just talk about the predicates over here? Because I told that predicates will represent some of the relations, right?
So IRE predicate is essentially a subset of DI.
Yes, exactly. So very good. Who's that?
I'm Devanjan.
Oh, Devanjan. Very good. So I of IRE this will be subset of D to the power. Is it clear to all of you? If not, I can just talk about some, like just take your arity down and try to see what are they actually, what I want to interpret. So is there anyone who couldn't realize what I am doing right now?
Oh yeah, can you explain this part again?
Bhargav.
Yeah.
Could you realize that why I am defining my L structure like that? Because I want to now define, I'm trying to start to give the meaning on those abstract structures, what I did in the syntax level, right? So we already observed that to give a meaning, I need at least one set where can I just talk about the what can I see, validity or satisfiability or truthness of the formula, given formula or something like that. So I need a set of which I will call a domain of discourse. Maybe I wrote down in a bad way. Okay, so that is understandable, Bhargav, like why I need to take help of some set. Is it clear?
Okay. Yeah.
Now what I am trying to
Understand the
say,
intuition.
yeah, I'm now trying to interpret my my logical languages in that D, right? Then only I can talk about the meaning and all, right? So what are the constant symbols? The interpretation of constant symbols will be some members of D. Like in group theory, what happened? Like my constant symbol is specifically, if I talk about some specific thing, it will become the identity, right? Now for function symbols. Why I took the function symbols? Because I would like to able to talk about the operations, right? And operations are nothing but the functions, right? So those function symbols will turn out to be that arity function in the domain. I mean, on the domain, right? So that is why I'm interpreting my function symbol with arity I as the function from d to the power I to d. In particular, just look at the group, logical language of group. I had one binary operations, right? So that is nothing but that should be play a role of the functions from d cross d to d, right? For some specific d, like if I want to, in fact, specify myself for the mo. Understand it? Bhargav?
Yes, ma'am. I had only doubt in the fourth part. The other three
Fourth
are
part,
actually
yes.
understood.
And the predicate symbol is what? That those are the PIJs. So those are the, I told that will be the player that will play the relation. Look at the logical language of order, because that contains some of the elements in the set of predicates, right?
Right.
And there I need to take care about the order. So order is nothing but a binary relation.
Right.
So that will be a subset of the D2.
Right.
Understand? Is it clear now?
Yes.
Okay. Is there anyone who didn't get it yet? Because it is, I'm telling that it is not very, what can I say, simple, who are actually seeing it for the very first time. Because we are actually overplaying ourselves with lots of symbols, right? So is it clear now to everyone? Like what I am talking about, that like what are the interpretation or logical, L structure. So now come to the example that will be much more clearer. So what is the L structure for order? So L structure for all those examples. Say the first example. So what it is? What is the meaning of that? Like, how can I just assign all the things over this? So of course I need a domain of interpretation, domain of discourse. And what else I need? I need one binary relation. Now, those P1, 2 was a symbol for a relation. Now I need a specific binary relation, right? So let's call it, say, a relation present in D. In particular, for example, what it is from our course of order structure from, lecture by Professor Sujata Ghosh. So it was, do you remember that I can talk about lattice and this, right? Or say partial ordered set. So a set and a partial order. That is in particular structure, L structure, right? And what about the second logical language? Say group. I need a domain of discourse, and then what? Constant and function symbols. So a specific member from D I need to pick. In particular, we used to call it E. Assign it like E, and some functions or operations over D, right? Say, call it some, like symbolize it like that. And what is the example of that? In particular, example of that will be what? And that is not a specific example, say better to write down this. Say I'm taking the natural number, L is again a arbitrary set or something like that. And I can take real with this order as well, right? So what are the example of this kind of things? What? Which set I am going to take as my domain of this? Integers. And 0. Can you give me more of L structures of that? Yeah. So, oh, you want me to do with that logical language and then the example you're talking about? Oh, you are just talking about the example. Yeah, that also can be taken. Yes. Okay. So, about arithmetic, what can you do? Piano arithmetic is about natural numbers, right? So we can take it like that. So, and also what Amit mentioned, you can take the mid similarities as well for the example, right? Okay, so that's it, the interpretation or L structure. Now come to the idea of is it visible, Amit, with that? Is it here? So what I need to do now? We already talked about that. What can we do for those logical language? So we already know what is the structure in specify, in particular. So what else I should do now? Tell me, because just think about the propositional logic, what we did actually. I need to just to the well-formed formula, or before that I need to take care of something. Terms as well, right? So what are left actually? So you do remember that in propositional logic, what we did, we just assigned some values for propositional variables, right? Now I need to assign values of what? To enable to talk about all the meanings and all, or in terms of first order logic about the model and all. So what I need to do? I need to assign values for the variables. Then only I can talk about, I will be able to talk about those truth or whatever for the given formulae, right? So now I'm just going to talk about the valuation, which is a function or assignment. Some people used to call it assignment. I don't know what Amit will call it.
Interpretation.
Okay, so in fact, interpretation also you can tell. So, or interpretation, let's say. So I just wanted to make a connection with the propositional logic part. That's why I'm just picking the words, whatever was used as much as possible. Okay, so valuation is what? That is a function from where to where. From where to where? How much time do I have?
Until 4.
Oh, it's a long time. Okay, fine. I do have a long time, so I can talk. Okay, so what function it is? Like from where to where I need to take the function? I already told it. So what it is? Set of terms, or I can just define this, because in propositional logic, just do remember, I just talked about I assigned the valuation on propositional variables only. Those are the atomic formulas, right? So P will be from set of variables to where?
The domain of the L structure.
Domain of the structure, because I will assign values of those variables to some point in the domain of discourse, right? So the rest of the terms I can define from that, right? So the thing is that what are the terms? Like we had, what are the terms? Can anyone recapture? Like variable, I already know where it will go in some sense. And so first we had constant symbols. So where it will go? The natural idea.
C itself.
C itself. C is where? C is in syntax, right?
Okay. Okay.
I need some value in D.
I
right?
of C. I of C.
I of C is a member of D, but C is not a member of D. So it is the part of the syntax now. So that's a natural idea to assign, right? So what? Oh, I see. Okay, sorry for that. I used to change those notations, and that is really forbidden in first order logic or any logical language. And I used to do that many times. It is not good. So next, the variables. So where the variables goes, I already know what it is. So actually now I am this is from variables to D, and now I'm extending it on the set of terms to D, right? And here I am just defining this, sorry. So I'm just like expanding my function to the terms. I told that if I assign the values for the variables, that is enough to talk about the valuation for all the terms. So I'm extending it like this. So where the X will come under that extension of this V?
V of X.
The natural thinking? Yeah, V of X. Yeah, because those are the elements of V. And what else I have as term? Exactly. So function symbols followed by. I would like to mention that here actually Amit told me that it's better to mention the bracket and comma in that, so that you will be not confused that which term is getting, like which argument will come where or something like that, to specify the order. But in general, my practice is not to specify this, but better to specify. So I do agree with him. So anyways, so I hope that you get what I talked about. So now tell me that what element it will give in the domain. Exactly. So for each T1, T2, Ti, I'm going to get this, right? V cap T1, V cap T2, dot, V cap Ti, right? So this is the tuple, I tuple, and what will be the value? Because I need a value in D, right? So I of Fij is an IRE function in D to the power, in D. So that is why the value of this will be assigned for this term, right? Now, what about the well-found formulas? So now we will be able to talk about that when a given formula is true or satisfied or something like that. I will just going to designate what I'll call it. So, and it is what specific? What specification I need to talk about the truth of a formula? Anyone? I already talked about it many times. So now I am trying to say that when a specific formula is true, like true under something, right? So what are the specifications actually I need to have at least to talk about the truth of a given formula? Interpretation should be designated, and what valuation function?
Predicates should be.
Predicates should be what?
P cap of predicate should be defined.
So the thing is that we can talk about the truth of a formula alpha under some interpretation, right? I need to specify my interpretation. Also, I need to specify which valuation I am working on, right? Because that I need to define. It is in my hand. Why it is in my hand? Because I can assign of my choice of values in D for the variables, right? And I can change that assignment. I'll get another valuation and so on. Just like in the truth table, right? I can have various valuations. So it is actually interpretation and this valuation dependent things, right? And this tuple is actually in first order logic or some model theory, I should say, is known as the model of that structure. Okay, so we used to say that alpha is true in a model in, that is this pair, I should say V caps in. Should I write down this interpretation I need or not? No, I think I need the interpretation, but maybe I can just remove this part. That will be fine. And will be denoted by, is it visible, Amit, this part?
Yeah.
Okay. Yes, like that will, like whenever I write down these things, I will talk about that alpha is true in the model, where in the model, the specification is what? I do have interpretations given and evaluation, right? Under that, when I can say that alpha is true in the model, right? So alpha can be of which type? Well-formed formulas looks like what? Well-formed formulas looks like what? What are the well-formed formulas? Okay, so you are going to talk about the formula looks like this. Say, better to specify this. If alpha is Ti equals to Tj, then or let I have this, and for this alpha, what I can say when I'll say that alpha is true in the model M? Any natural idea when I can say that T1 equal, I mean Ti equals to Tj? What is the idea?
The valuation of Pi is equal to the valuation of Pj in the model
That is
M.
the natural idea, right? It is true if valuation of Pi equals to valuation of Pj. All of you agree with that, right? What is the second type of formula? So alpha looks like what next? Because those are atomic. So atomic one, let us finish and then we will talk about the composite one. So what else atomic formula we do have in our hand? Predicates, right? So it looks like this. Then when I say that alpha is true in this model, when it will be true in the model? What is the natural expectation? Predicate actually tells you what, like it represents what in your structure? Yes, then that means what? What should be done? So you are talking about this, right? So V cap say. Yeah. Then this is kind of a tuple say, right? So what will be my demand? Interpretation of that. That means this will form a relation in it, right? It will belong to the interpretation of Ij. So that is the idea. All of you are agreeing with that? For the atomic formula at least, when the atomic formula are true in a model, right? So now what else? Alpha can looks like what? Next type of formula, actually I removed everything because I had no place to keep it. So I hope that you remember what kind of formulas I do have. Or say, yeah, alpha is beta in arrow gamma that you are taking, right? So where beta and gamma are again formulas. So when I'll call that alpha is true in the model, when alpha looks like that, if Now I can talk about, I already know because these are the sub formulas in some sense. So I know about the, say, truth of this beta and gamma, and in terms of that I need to define, right? So we all always, wherever we define something, we define recursively, right? So let we know that what are the truth value of, truth of beta in that given model, and say that when alpha, and other than you, any one of you can tell that, because he is giving all the answers, maybe he knows it. I don't know. Anyone from the online participants?
If beta, if M satisfies beta, beta implies M satisfies gamma.
That means actually, in other words, whenever alpha is true in M, then beta should be true in, sorry, not alpha, but beta, then gamma should be true in M, right? The same model. That means what? If the am I correct? I'm writing it down because you already had enough idea about the implication from your propositional calculus class. So can you see that why I can write easily the second statement as well? All of you can understand?
We have 10 minutes.
10 minutes more. Okay, thank you. Thank you so much. I can wrap up, I guess. Okay. So anyone? So we already talked about syntax and we are talking about semantics right now, right? So that was the goal of my total lecture. So I can finish, but you need to give me the answer, because I need to talk about all type of formulas, right? When they are true in some model. So what is the next? Next alpha will be of the form not beta. Yeah. So in this case, alpha is true in the model if
M is not equal to beta.
Yeah, alpha is not true in the model, right? So not alpha but beta. Is it the case or I'm wrong? Understand? Now come to the main place. Because those were my, like somehow bit looks like the propositional things, how we assigned the valuations for the composite formulas and so on. Now it is new to us right now. When
I have a doubt in I of PJI. So PJI, I of PJI belongs to D, right?
Belongs to I of Pij.
Yeah, I of Pij belongs to D or D power n.
E to the power I.
D to the power I.
It's a subset of that, right? Because there's a relation.
Okay, fine. Cool.
It's a subset of that. And I want to interpret as a relation.
Yes.
Model, right?
Yeah.
So now tell me that if I have the formula alpha of the type this for all x beta, because that is left only, right? And other things I can define, and I didn't abbreviated it. Actually, we can abbreviate this thing like that. There exists because there is this x is also important in mathematical languages, and we used to do work on that many times. So that is nothing but the abbreviation of this. I think after giving the meaning, it will be much more clear to you why it is so. Okay, so if I tell that, so when I'll utter that for all x beta is true in M, what to do? Here you could see that I talked about, I assumed that I know the truth of the sub-formula in the model, and then I used this idea and then I talked about it, right? About the truth of these compound models. So what about the compound formula? What about the for all x beta? How can when can I will be able, when I'll be able to talk about the that this kind of formula is true in that model? I already started with that example, right? So what is the natural idea to do?
For all x beta is in model.
For all x?
Beta is in model.
Oh, that I don't know. I never defined. You are talking about for all x, beta is in the model. That means what? I don't know it.
Okay.
I never defined these kind of things. Can you explain what do you mean by this?
They're trying to say that making a statement in the meta language that for every variable x n should model beta.
Okay. So okay, anyways, so what do you mean by the meta language?
That we're making a statement that if for every variable x, if it happens to be a variable n model beta for every choice of x.
Choice of x means from where? That you need to specify.
The valuation.
From the valuation, how can I choose x? Yeah, I need to check that for all the points in the domain of discourse, beta is true in M or not. But how can I, what can I say? How can I express it? Just like there. If, what can I say? We only know that how to assign values from D for terms, right? And what are X? What are beta? Anyone from the online participants?
Can you say for all x in the domain of discourse, we have to have that beta of x must be true in the model. So then when you substitute x in beta.
Yeah, that means you want to change your model in some sense. Or not really. I really didn't get you. Can you repeat it again? And who's that?
I mean, if you write for every variable in the domain of discourse,
for
or
all
for every element
for
in the
all
domain of
elements,
discourse,
D in D, yeah.
when you substitute D in beta, it must be true in the model where x was.
Substitute D in beta at which places?
Where x was originally in it.
So in some sense, you want to talk about this, right? M is, I mean, beta, wherever x occurs, I'm just substituting D there, right? This kind of things.
Yes.
This should be true in the model. That is your idea you are talking about. And that should happen for all D. That is your suggestion, right?
Yes.
All of you are agreeing with that? Yes. How many of you are agreeing with that? But I specified already that I do have valuation functions from set of terms to D. I don't have the other way around things, right? Here what we are doing actually. Oh, who gave me the answer? Okay. So I cannot see. Okay. Clarice, can you understand what I am trying to specify right now?
I'm not sure. I don't think so.
What I am talking about, right?
I don't think I understand.
You can understand what I am trying to say. Or not really?
I don't think so. Sorry, I don't think so.
Understand. Okay. So what I am trying to say, what you did actually, you were trying to put D wherever X occurs in beta, right? Right? And the thing is that X are what? X are my terms, right? And D comes from where? The domain of interpretation. Sorry, the domain of discourse, or domain of interpretation, whatever, same thing. Right?
Yes.
but it may happen,
Okay.
like you can understand that my set of term is what? Cardinality of set of term is what? Can anyone tell me that what is the cardinality of set of terms? I didn't talk about it. Oh, it's already over, I think, my time. Oh, sorry. So there is another tutorial, right? So can I take some few, 5 minutes more? Then I can just end with that. Okay, so the thing is that you can understand that my domain of discourse can be anything, right?
Yes.
A very big set, right? Uncountably many. But my set of terms are countable because I allowed countably many things here. And I was just concatenate those things to form those strings. So that's why I will be in danger because I don't have, I don't know whether I can make a mapping from the D to the set of terms, but I do have the mapping from the set of terms to D, right? So what else can I do as I don't have time? Otherwise, I could ask all of you what to do. So I can change my model in some sense. Like I'm going to take M dashed, where M dashed will contain the set of interpretation. The interpretations together with, I'm just changing my valuation function now. So how I'm changing this? I'm changing it E prime over y will be equal to V of y if y not equals to x, and wherever x occurs, I'm going to assign D. Understand the model, how I changed it? I just changed at one place, wherever x, like I'm just assigning the value of x as D. And now I can talk about that if my beta is true for all in that M prime. So I can specify because I'm changing x to D, I'm assigning x to D here. So I can write down in that way. And then I can say for all audible? Am I audible?
Yes.
Okay. Okay. So what I was trying to say that could you realize the difference between what I forget the name again. What's the name of her? Achha, Clarice. Yeah. What Clarice proposal and what I wrote on the board. Could you realize the difference between this? Because you could see that in the right hand side, I make the mixture of the elements from the semantics and syntax in some sense, right? That I am not allowed to. And also I told that what could be the problem if the domain of the discourse will be uncountable, because I never specified that my domain of discourse should be countable, whereas I already specified my syntax, and that's why I already know the set of terms is countable, right? So I will be in danger to take care about all the situations if I use the proposal of Clarice, right? Is it understandable?
Yes.
If not, please try to think about it because it is very much needed to understand, I should say. And I think that's it for today. Thank you for listening.
Vitali. So we'll end this session here. We'll have a tea break of 10 minutes, and then we'll come back for the tutorials in Boolean algebra and stone dualities.
So I'm just continuing with some of the informations. Like in propositional logic, what you saw, that we talked about the completeness and soundness and all, right? So the thing is that like here we can do the soundness and completeness with the help of those definitions. Whatever I did, it's really very formal, I can understand, and it is very hard to digest. That I also agree. So the completeness was first given by Gödel, that Mohadi already explained, mentioned in her talk in that morning session, and later on, I think Skolem, right, Amit? Who else gave the proof of that completeness of first order logic? That's Henkin, sorry. Henkin also gave the completeness proof. And the thing is that while talking about the completeness and all, we actually took the help of that Lindenbaum-Tarski type of algebra, what was Boolean algebra for classical logic. But here you can see, other than the connectives, I do have that existential quantifier. And people were trying to algebraize this kind of logic in algebra sense. And then I think Tarski came up with an algebra, very nice kind of algebra. This is known as cylindric algebra. Yeah, someone wants to talk? Oh, okay. So, and I already put it as a project. If you are interested in, you can have a look at it, that what is the cylindric algebra. It is kind of extension of polyadic algebra, which was, I think, proposed by Paul Halmos. So that I wanted to say to you. So if you do some project on it, it will be very good to see that how that algebraization is going on for this first order logic. Okay, that's it. Thank you so much for listening. It was not working. कितनी बार बैटरी चेंज हो रही है? अच्छा, okay. তুই তো জানিস কোন না? Can you hear me, guys? I'm assigning you, don't worry. Can you hear me, guys?
Yes.
Okay, very good. So now we are going to start with the tutorial session for, stone duality and propositional logic. So how many of you are here right now? 13 of you. Okay. So can you just open your videos, because we want to see who are there. I never can see many of you. Don't you have the videos? I don't know any one of them. Oh, Shilpi Kumari, right? What about the others? You really don't have any other options. You need to just turn on your videos. Okay. Anyways, so today you need to see that wherever you are facing what can I say, difficulties in the lectures of stone duality, stone representation theory, and propositional logic, you may ask, and Prashanjit will take care about that online participants, and here Bidhan is here, so he is going to take care about the other students here, and if you need more help, we are here. Okay, so try to have a look at whatever was is the course material is given or not really? Course material is given. Okay, in the website you can find the course materials for the lecture, whatever covered by today morning session and yesterday. So try to have a look. If you have any problem with any of the theorems or the proof or concepts, please ask Prashanjit. Okay, Prashanjit, please continue. You do have this?
So if you have any questions, then ask me. So in the tutorial sheets, the problem are basically some standard results. So the proof you can find any standard books of that is theory. So I don't know how to proceed. So if you have any queries about this, so please ask.
You can talk about the notes what Mohad mentioned. You are talking about propositional logic or stone duality?
Anything.
Please involve them with some of the problems. Maybe she gave the exercises, right? At least talk about one exercise they can just solve and see. But,
So go through the tutorial which the tutor sent to you. So the first one is about the Boolean algebra. So it's what so someone anyone think about it? Hello?
Yes.
So can you give the idea of the proof? Hello? So
সব করে দিচ্ছি না, একটা ওদেরকে করতে বল, একটা করে বল যে পারছি কিনা, একটা মেনশন কর কোনটা করতে হবে।
বললাম তো কেউ কিছু বলছে না।
না বলতে বল। ওকে, তাহলে আমি জিজ্ঞাসা করছি। And this is given, no? কি করতে দিয়েছে?
এটা কি দিয়েছে মানে আমি জানি না তোমরা সেন্ড করেছো
আমি তো জানি না কিছু। না দেখছি। এই অন্যায় বলছি যে ওই টিউটোরিয়াল শিটটা করা হয়েছে? হ্যাঁ ওটা আপলোড করা আছে, ওটা পাস করতে হবে।
So do you have the tutorial sheet? Hello? Anyone is there?
Yes.
So do you have the tutorial sheet?
Yes.
Okay, so do you want to some a proof of the results given in the tutorial sheets? Or
I was just looking at the question.
okay. Or any questions about stone duality?
Is there anyone who already solved the problem number 1 in the problem sheet? Can you hear me, guys? Hello?
Yes.
Yeah, is there anyone who already solved the problem number 1? Are you doing that or not really? Are you with us?
I was looking at the second question first.
Okay, fine. So second question is solved by you or not at all, really?
Yes,
No.
I have ideas. Like I think I am right.
So do you want to explain it to others as well?
Yes. So
Please
like,
do that.
it is like H is an isomorphism. So if like A is an atom in B, so if like any two elements are related in B, then they will also be related in B dash, like in the same way. So if A is an atom in B, then HA will be an atom in B dash. Since it is an isomorphism, the relation will hold. Like if X relates Y, then it will also be true that Fx is related to Fy.
Can you repeat this once again?
Like if A is an atom of B, so there is certain condition like if B is less than A, then B is the bottom element.
First A is a non-zero element, and if something bottom of A, then it's equal either equal to B, A or zero. Yeah. Yeah.
In same way, we can say the same thing about B dash. Like if like A is an atom of B and HA is in B dash, so if HB is less than or equal to HA, then either HB will be equal to A or less or the bottom element.
Why so?
Because it is an isomorphism.
So isomorphisms means this preserves order.
Yes, means if X is related to Y, then Fx is related to Fy. Like it will be order embedding.
Yes, order embedding. Okay. So it is order embedding. So something if B is less or equal to A, then H of
B is less than or equal to H of.
Okay, from there on if and only if condition. So using that you can prove this.
So, am I right?
Yeah.
Same way, the second part of it can be proved. If B is atomic,
So,
and only if
the others people except Lavish, do you understand?
What Lavish actually told? I mean, explained.
I said like if A is an atom of B, then there is one condition, like if B is less than A, then either B is less than or equal to A, then B is either the bottom element or B is equal to A.
Yeah.
So the same thing will be true in B dash space, because if X is related to Y, then Fx is related to Fy.
X is related to Y, then Fx related to less or equal to,
H-
yes, the order embedding here.
So that's why if B is less than or equal to A, then H of B will be less than or equal to H of A. So like it will be true.
Oh, except Lavish, are you guys there or not?
Just call someone and ask that what question
Yeah.
you solved already.
Aditya, are you there?
Yes.
So do you have any query, any questions? Or you, yeah?
I'm just trying.
No, you're
Which
trying.
one you are trying? Aditya?
Which one you're trying?
Just let us explain.
Huh?
Oh, you couldn't follow what Lavesh wanted to say?
All that bits trying to cope up with.
Okay, so if you have, further queries, ask Lavesh as well, okay?
Okay.
So what about all of you get the idea about the first question?
Suresh, hello, are you there?
Yes, sir, I'm trying.
So you are trying which one?
The first one.
First one. Okay.
What about the second question? So who solved the first question? You can see on the board, right? It is already solved. Can any one of you check whether it is correct or not for the first question? I cannot hear any one of you. You should talk with me, right? Otherwise, how can I know that you are doing something? So I told you to open your video and show your faces. Otherwise, I can't realize that. What are you doing? Are you sleeping or eating or what? I also want to see. Yeah, very good. So first question, who solved among you? Nupur already solved here on the board. So try to see whether she is correct or not and give me the answer. So can anyone tell me whether it is correct, the solution over the board? Consider yourself as a proof checker and just do that, like prove whether that proof is correct or not. You already you know that what are true in that theory, right? So do it and tell me that whether it is correct or not.
So Nia, do you want to say something?
Am I audible or not really?
Hello?
Yes, you're audible.
But am I audible?
Yes.
So why you are not giving me the answer? I can't realize that whether I'm audible or not. Is that proof correct written over the board?
It looks correct.
It looks correct, okay. What about others?
Yeah, it looks correct.
You shouldn't say it looks, because we are the logic people right now. You already had enough, what can I say, already have enough knowledge about logic. You should say, and we are talking about classical logic. You should say yes or no. Don't tell that it looks. if I will talk about fuzzy logic, then you are allowed to say this kind of things. Don't do it now. So yes or no? What about Shilpi? Shilpi, Abhijit, are you sleeping or are you at all in front of your computer?
Yes, yes.
Okay, so tell me that whether the proof is correct
Yes,
or not.
it is correct.
Yeah, very good, Abhijit. At least you see, we tell a definite answer. That's good. So what about the second problem? What, who explained it? Prasenjit?
Lavesh.
Lavesh. So Lavesh is not here. I can
Yes,
see.
yes, yes. Yes.
Oh, that's Lavesh. Okay.
Lavesh is the second problem is atomic.
Yeah, he already explained it properly.
I explained the third one.
Third one.
Oh, you explained the third one. So what about the second one? Who can give the answer of the second one? I hope that those are not that complicated.
Second one is already discussed in the class.
Is it?
Yeah.
Then they should be able to give the answer, right? They are not giving the answer to us. What about the second one? As Prasenjit told me that it is already covered in the class.
No, it wasn't covered there.
Okay,
I
then
mean,
try to
ma'am just
say it.
gave a statement. So I'm thinking about the proof.
You are thinking about the proof, okay?
If it is not atomic, then there will exist an element that does not have an atom below it. So for every element that is below it, there will exist a smaller, strictly smaller element below it. So by induction, we will construct an infinite chain that would contradict the finiteness of.
Yeah, very good.
Yeah.
So all of you get the point? Who told it? Who explained it? Sanjay.
I am Suyash Srivastava.
Oh, okay. Shwesh. Okay. Thanks a lot for that. So all of you get the answer explained by Shwesh?
Yes.
Okay, very good. What about the fourth problem? Because third problem is already covered by Lavesh. So what about the fourth problem? I also need to see. What is the fourth problem?
Actually, what I told was not third problem. It is little later. Like there is no numbering in the tutorial, so I.
Oh, there is no numbering. Oh, yeah. What about the first problem given in the prime filter theorem? This one? Those are the problems or those are? Let me see. আচ্ছা এটা বলেছে already, right? ওটা জিজ্ঞাসা করি তাহলে ওটা বল ওটা জিজ্ঞাসা কর
So hello. So anyone try that problem that for any prime filter if there exists a homomorphism such that if the filter is collection of all x such that h of x is 1 and the next one. Anyone try this? I can give you a hint. Think about characteristic functions. Do you know the characteristic functions? Anyone know?
Who doesn't know what is a characteristic function? All of you know that?
Which problem number are you talking about? Like, there are no numbers. So
that the problem that for any prime filters, if there is a homomorphism HB to the two-elemented Boolean algebra, such that if is x belongs to B, such that h of x equal to 1 and the next one.
Yeah, okay.
So it is very simple. You can think about characteristic functions and try to show that it's a homomorphism or not.
Can anyone explain what is a characteristic function? Vijay?
Like
What is the characteristic function?
A characteristic function
Yes, characteristic function is like in some, if you given in a set, the characteristic function will put the value 1 if the element belongs to the set, or otherwise it will be 0.
So characteristic function of a set I need to specify, right?
Yeah.
Okay. So why it is, we need to do what? It is a homomorphism. Is it so? Yeah. So why it is a homomorphism? I hope that shouldn't be very hard, right? What to check actually to show that it's a homomorphism indeed? What I need to show actually?
I mean, to check a homomorphism, that it will like the operation will it will be expanded in case of the operations.
No, it need to preserve the structure.
Yeah, the structure will be. Yeah, exactly.
Yeah. So what explicitly you need to prove actually? That will be your answer only. So what you need to actually prove? Homomorphism from where to where? Characteristic function is a homomorphism from where to where? You need to specify the domain and the codomain, right? I mean the structure of the domain and the structure of the codomain, so that you will be able to talk about the homomorphism. So where you are doing that?
From B to 2.
B to two elemented Boolean algebra.
A means 0, 1. Characteristic function is a function from where to where? First specify that.
From B to B is the Boolean algebra and 2 is the 2-element.
2-element Boolean algebra. I can just see 2-element set, and I can just impose the what can I say, those operations, and that will become a Boolean algebra, right? So now what I need to show?
First you have to define the characteristic functions.
Yeah, characteristic, he already told what it is. And now tell me that why it is so. That means what we need to show now, that H of A join B or union B, whatever you want to say. I'm better to talk about join. A join B equals to H of A join H of B, right? Am I correct?
Yes.
Yes.
So where that H of A or H of B goes? What are the values of those? Am I understandable what I am asking actually?
Yes, 0 or 1.
So how to check it? How to check the homomorphism things? Like why the characteristic function should always be an homomorphism? Is it the question? Yeah. Why it is so?
The question is that for a given filter F, you can define a homomorphisms H such that F is X belongs to B.
Okay. So in particular, you have to show that, right? So why it is a homomorphism? Let me know. Prashni, can you write down on the board so that they can understand and give you the answers? You can have that color mic and talk with them. If I need, I will just touch it. So Prashanjit is writing down whatever is needed to prove, and I ask you to help him as well. Like it is not the case that he is going to write down everything for you. You should also tell him what to write.
Okay, so the problem is that for a given filter, you have to find a homomorphism from.
I think better write down the problem first. That will be better for us, because there is no problem.
Problem
Numbers
okay.
are given, na?
I write down the problem. So you have a Boolean algebra and you have a filters for that Boolean algebra, and you have to find a homomorphism from V to 2-elemented Boolean algebra. Okay, H such that F is defined by that X belongs to B such that H of X belongs to 1. So to solve this problem, hint is that think about characteristics functions. So now tell me how we proceed.
The question is, does it satisfy all the properties to be a homomorphism, what he proposed now?
So
if you are not giving the answer, Prashant is not going to write anything else. You need to tell what to write. Anyone? Prashant asks what to write.
what to write? Anyone, please? Okay, I'm writing the functions first. Okay, we denote by h of f from b2 to 1 and define f of x is 1.
For x.
X belongs to where?
Huh? X in f. X
F.
in f.
Yeah.
And 0 for x not in f.
X not in f. Okay. So is it a homomorphism?
F is filter here, right? Sorry, I'm missing the question.
F is a filter. Okay. So
so of course by notion of filter, like it is closed upwards. So for any two elements x.
No. It's nothing about filters closed upwards. So to show homomorphism, what have you okay.
Anand, can you help O3 and help writing Prosenjit? That what to actually check?
So we need to show that this is a homomorphism, right? Like a
yeah.
And so like negation, I think it's clear because it's a prime filter. So if a element is here, then its complement is not there. And likewise, since it's upward closed, I think it's closed under and the wedge operation. And I think intersection will follow from these two.
Can you repeat?
So since it's given that it's a prime filter,
yeah,
I think it's a homomorphism under negation.
So you should
in the complement.
Yeah.
And like so prime filter means that either so if a set is in the filter, then its complement is not there and vice versa. So I think so this will be a homomorphism. Like so if h of not x is equal to not h of x.
Okay.
This is true because it's a prime filter.
Okay. Why so is that?
Because if we're saying h of x is 1 if x is in the filter.
Okay.
So h of not x means that x complement is not in the filter.
Okay.
And so in a prime filter, like either
as it is prime filter. So x is 0, which is not of hx. And what about that meet?
So I think this will follow from the fact that it's a filter and it's upward.
Yeah, this follows
closed upward. Yeah, that's what I'm talking. This is closed upward, so that's why for any two x, the intersection if x and y both are in from f, so we can say that like h x not x meet y or x join y also in f.
No. Why
you
use upwardness?
Okay, I think this might be finite intersection property.
Yeah, it follows from that if it's a filter and is closed under that meet.
Yeah, meet. Yeah.
Yeah, this is from there.
Yeah. So yeah. So
for this you need. Okay. Now
this I think will be upward.
Yeah.
Closed.
Yeah. So I think you understand the answer.
Very good.
Okay. Okay. So now try the last one. So use the infinite sets.
We can use that. I can just change it on this.
Can I remove this solution?
Yeah,
Yes,
you can remove. Yeah.
Okay. So given is that U is an infinite set. Okay. So, and also given that F is a collection, okay, where that A is a subset of U, such that A is either finite or cofinite. So you have to show claim is F is a sub-algebra of the power set Boolean algebra. Okay. So are you guys thinking about the problem? Hello?
Yeah.
So think about that. Anyone from the offline can also do. You want to try? So Nitish want to try. Yeah, last question. Is either finite or cofinite. So you have to prove.
Like if you're considered
1 minute.
like if this collection of finite is cofinite. And like if we're considering that this collection of all cofinite and finite algebra, it means their complements exist in each other.
Yeah.
Its complement exists, and now it
Right.
is
I don't. To check one by one property.
To check for algebra, we have to check that if it carries all the operations.
Yeah.
So like for union and intersection, it's obviously carry because it's
Why? Not obviously. You write down the proof.
Okay, for finite intersection will for the finite sets, the union will be inside it, and so for the intersection will be inside it too, right?
Okay.
And same goes for if it's a cofinite set, then it will
Union and intersection is so now the problem is if one is finite and one is cofinite.
And they are complements of each other, like so like for the union, intersection, and complement, the both are each of operation exist, and like and we are carrying our x and phi jo our entire set and phi.
So x and phi.
No. Like we are carrying all the operations, and it is closed in itself. Like all we have to see that.
So x and phi is there or not?
No, x and phi are not there. X and phi are not. Phi is there, but x is.
Why x is not there?
Wait.
What is
X should be there.
Yeah.
Phi.
X complement is phi, and phi is.
Yeah, x and phi are there, right?
Yeah. So
yeah, x and phi are also there.
Yeah.
But it is closed in P of B. Like it is all of the elements of P of B, like all of the elements it has are inside P of V.
Okay.
Right. So it is closed inside P of V, and it
which
carries
is closed.
Our F.
So, okay.
Is enclosed.
If F is closed under P of B means
all of elements of F belongs to P of B. Elements of P of B.
Okay, the subset.
And it carries all the operations from it.
Why so?
The intersection, complement, and
so
union.
you just clarify that for if say A and B belongs to F and both are finite, then nothing to prove.
Yeah.
Because intersection of finite and union of finite are finite. Yeah. So if A or B are cofinite, then you can check union of cofinite set is cofinite intersection of cofinite.
Intersection.
So now verify that if A is a finite and B is a cofinite, then A intersection B is a cofinite and not finite or cofinite. So so for this case you have to verify this two belongs to F. So my question is why?
This is finite and this cofinite. Then this is obviously gonna be cofinite.
Which one is cofinite?
Yeah.
Yeah. Okay. And this?
This one will be cofinite too. Yes.
Why? So A intersection B.
Can
Online participant suggest what the set is?
It is obviously finite.
Yeah.
Finite.
Obviously
Obviously
finite.
finite. Yeah.
Okay. So it is finite. So this is belongs to that F.
And the union will be cofinite.
Yeah. The union is cofinite. So F is closed under union intersections and complement is
they are each other's complements.
So the complement
like they carry all the operations and it is closed inside it.
Yeah.
P of V. So it is a subalgebra of it.
So online and offline student understood that what we have discussed already.
Yeah.
Okay. So now I ask to the online participant, please suggest some problems which I can solve for you from the tutorials.
Sir, about the Lindemann-Tarski algebra.
Yeah.
Actually, can you elaborate that? I can not totally satisfy.
What is your question about a linear Tarski algebra?
Actually, how an atom is can write up like this something.
How atom is?
Every atom is of the form like.
Okay. So, ma'am, in the class, ma'am, talking about some CDNF. You remember that?
Congruent.
Yeah.
Congruent classes, no?
In Moha Banerjee's class. So he talked about some CNF and CNF that any formula can be written as or any formula can be expressed as a some conjunction of disjunct that that I1 equal to n and sigma I pi. So do you remember that?
Yes, sir. Yes, sir.
Yeah.
I remember this.
Okay. So now that alpha is some join of these disjunctions, conjunctions. So so each I n and sigma I of pi is less than alpha, and already he mentioned that this is this class. Sorry, I have to mention as a class of this. He already mentioned that this class is not 0. 0 means that I equal to 1 to n sigma I of pi. This is not equal to that. Okay. So now you get the idea why actually atoms are look like this. Hello.
Actually not.
Actually not.
I'm not really satisfied.
So if alpha is an atom, then what is the first condition?
It will be a greater than 0 and all the members will be less.
It not.
It is not equal to 0. And, okay.
Yeah. So okay, and second condition is that if beta is lesser or equal to alpha, then either beta
is equal to 0 or
0
beta
or
is equal to alpha.
beta is equal to
Alpha.
alpha. So now you given that alpha is an atom, and we know that alpha can be represented by this.
Like this.
Okay. So alpha is non-zero. Okay.
Okay.
So at least one of the component must be non-zero.
Yes.
Yeah. So and we know that each component is lesser or equal to alpha because alpha is join of that.
Okay,
Yeah?
sir. I got it.
Okay. Thank you. Okay. So others people got understand the what I explained now.
Yes, sir.
Yes.
Okay. So any others problem?
Well, sir, actually, regarding the prime filter theorem,
Yeah.
so I know the topology, the ultrafilter version, where we have to take the union of all the subsets of we choose a filter, and then we consider the union of all subsets and form a chain, and there exists a maximal element by Zorn's lemma that type. So
Yeah.
here, this proof is also like analogous to that proof. Yeah. Like.
Yeah. So
Okay.
I just sketch the proof.
Yeah.
What have to so there exists a filter. Okay. The idea of the proof, take the proper filters. Okay. So say F is a proper filter, and consider this collection. So C.
Yeah, the filters which are subsets of subsets of F
So,
and their union.
the filters, suppose this is a filter of the Boolean algebra such that F is a subset of F1. Okay. So first check this is non-empty. Okay. Then who suggests that chain?
Yes, sir. A3.
A3. So A3 just mentioned. So take then show that every chain has upper bound. Okay. Then use the Jones lemma. You got a you get a maximal element. Element of C, and try to prove that this maximal element is the prime filters. Okay. So actually same idea. You are right. A3.
Yeah.
Okay. Anything? So in class, ma'am already so many times used that result that if A is an atom, then for all X either A lesser equal to X or A lesser equal to complement of X. So anyone, can you give the idea of the proofs or help me to prove the results?
Sorry, can you repeat again? I missed the question.
Okay, so B is a Boolean algebra, and X belongs to B. Okay. So and A belongs to atom of, so we denote the set of atom by this A of B. Okay. So then claim is that either A lesser equal to X or
or that A will less than X complement. Yeah.
So please, someone tell how do you proceed?
Sir, if X is greater than 0, then by definition it will obviously imply like A is less than or equal to X. And if x is equal to 0, then
I did not get your point. Please repeat. If x is greater
is
than 0.
greater than the bottom element. Okay.
X is a bottom element or x is greater
No,
than?
greater than
Yeah.
greater
Okay.
than bottom element.
Okay. Then
Sir, bottom element I will define by 0 or 1. So okay. So by the definition of atom. Okay.
yeah.
Okay. By the definition of atom, it will be actually A is atom. So x will be greater than or equal to A, or x is equal to A.
Why? So
A is atom na. So
no. Take this Boolean algebra. This is 1, 0, A, B. So if you take, so A is atom, B is atom. So if you take B, okay, and B is atom, and if you take A, then A and this in that Boolean algebra, these two elements are not comparable.
incomparable. Okay.
Okay. So think about in that way that x meet x is 0 or x join x is 1. So using any of this equation, you can try, you can think. And you have distributivity law. So you have distributive law, and one more thing is that A lesser equal to B. This is called connecting lemma. A is equal to B if and only if A join B equal to A, or equivalent is equivalent to A join B equal to B. Okay, and distributivity of Boolean algebra, you can solve this. So think about.
Hello.
Hello.
Can I do this?
Yeah, you you are
online.
Yeah.
So first, A is what is that? If A is not less than or equal to X.
A is not less or equal to
X. Assume that.
A
Then
is,
I'll prove that A is less than or equal to XC.
okay.
Okay.
So A is less or equal to X complement.
Yeah.
Okay.
So A is not less than or equal to X, and A is an atom, means X is either is equal to the bottom element. X is either is equal to bottom element, or X is not comparable to A. Is that okay?
No.
So A is not less than or equal to X. Okay. Yeah. For either X is less than A or X is not comparable to A.
X is less than A.
Or not less than or equal to, less than A.
Less than A.
Or X is not comparable to A.
X is not comparable to A.
This is coming from A not less than or equal, or X not comparable to A.
Not comparable to A. So how?
Yeah, write that also, no? X not comparable to A. Not comparable. So in the first case, if X is less than A, then X is bottom element. Okay, X is bottom element or X not comparable. If X is bottom element, then X complement is top.
Okay.
Okay, that means A is less than or equal to X.
A.
This will give you A less than or equal to X, right?
A less than equal to
X.
X complement.
X complement, correct. Yeah. Yeah. Now, second case is that fine? That is the first case done. Then when X is, what is that?
So now,
X is the bottom.
now X is not
Yeah, exactly. Yeah, yeah. So now take X is not comparable to A and write A is equal to A intersection top. Take A. Excuse me. Take A is equal to. A is equal to
X.
A is equal to.
A is equal to
A intersection top. Can I write like this?
A intersection
T.
top. Okay.
Now top can be written as X union X complement.
Yeah.
Okay. Use distributive.
Yes.
The first one is A intersection X. Their uncomparable means their intersection is 0, I think, right? That is bottom element.
Now tell me what?
A intersection X is T bottom element.
A X is bottom element. Why?
A intersection X. I assume now A X is not comparable to A.
Then?
What's the intersection of the two?
I don't know. Not comparable. I say that if comparable, this to happen. Not comparable, so I.
Oh, okay, okay.
But you are,
not comparable doesn't mean this is the bottom element, right? A intersection X need not be bottom element.
No, no. You're right. Direction. So now use that A is an atom.
A is an atom. Okay. A intersection X should be A.
So
or empty.
No.
Or bottom.
Yeah, yeah.
Okay. So A is not. So this should be bottom element.
Which one is bottom element?
A intersection X.
So A intersection X, Y bottom?
Because X is not comparable to A. So it has to be less than A.
So no. First, from there, what we can say that A intersection X is less than A. Okay. One thing is, and A or
sir, it cannot be equal to A, right?
Why not equal? Why?
The case when X is not comparable to A. Sir, we are looking at the case X is not comparable to A.
Okay, X is not comparable to A.
So then A intersection X cannot be equal to A, right?
Okay.
Is that true?
Yeah.
Then it should be bottom element.
Yeah.
So A intersection X is bottom element. You substitute that here.
So this is
bottom element. Substitute that in that distributive after the distributive.
Okay.
Union
Yeah.
A intersection X complement.
Yeah.
So that is just A intersection X complement, right?
A intersection
X complement.
X complement. Yeah, right.
So A is equal to A intersection X complement is what you get.
Yeah.
That gives you X is X complement is
from,
greater than or equal to A.
Using that, you can say that
A is less than or equal to X complement.
A is less or equal to X complement. And similarly, if you say that X complement is not comparable to A, or if this is
I mean it is the end of it, I think.
End of?
End of the proof.
Oh, okay. Yes, this is end of the proof.
End of the proof, because if A is not less than or equal to X, I proved that A is less than or equal to X complement. End of the proof.
You're right. You're right. So other people understand the proof? The explanation is clear? The others?
Yeah.
Okay. So who tell the solution? Okay, got it. Thank you. Okay. Now anything? So what problem do you want to try now next? Tell me. Which problem do you want to try? If you do not suggest any problem, then we can stop here. Hello, I am audible. Hello.
Audible, sir.
So, any suggestion? Which problem?
Yeah, I'm trying the next problem. So
Next
need
problem.
yeah, I'm trying that once. Need a couple more time.
Which one? Tell me.
The problem just we discussed, and just the next one. So
Okay, B is a finite for any x, then x equal to this for all atoms I. Okay, so for finite Boolean algebra. Okay, try.
Can I have the list of problems?
Which?
I came late, so I don't have the list of problems.
Oh, you don't have the list of problems?
No.
It is uploaded in the website.
Oh, okay, fine. Fine, I'll get it.
Okay. So, who want to try this problem? Who? Atri. Okay.
yeah, sir. Yeah, I think I got it. Yeah, it's easy actually, not that hard.
Okay, so tell me what is the proof?
Sir, sir, here I think the AI are all atoms. So yeah.
B is a finite Boolean algebra, and what I have to show that for any x belongs to B, okay, x equal to join of I belongs to 1 to n for some for all where AI is a for all atom AI below x. Okay, now to tell the solution. How do you proceed?
If suppose that for any I mean like AI is the atom is greater than x, that will contradict the for our first consideration that x is equals to the join of AI, na? Because
no, why you are assuming that?
Suppose sorry. Suppose yeah.
You are given that AI is less than x. So a hint is that take these sets. Okay, A belongs to atom of B such that AI is equal to x. Okay, and take if this is S, take x. So try to show that x is lesser or equal to that, and u of x is lesser or equal to x.
I think one side is trivial.
One side is trivial. Yeah, which side? This one is.
P of S is less equal X.
Yeah, this one is trivial. Now try to show these directions that X is less or equal to V of I equal to 1 to N. So A is atom. So Atri, how do you proceed?
Well, can you just repeat the last step? Actually, I got missed somewhere.
So you have to prove this one. So for that, you have to show X this one and join of that AI is less or equal to X. Okay. So this part is trivial because all AI are less.
Yeah.
So this one is trivial. So you have to prove this one. So tell me, anyone from online, offline? Tell me. Give some idea. This is one that you want to try that every finite Boolean algebra, for any finite Boolean algebra, that X, any element X can be written as a join of the atoms below that X. Stop. Okay, so think about this in home. Okay. So we are running out of time. So we stop here for today and think about the.
Yeah, sir.
No. Okay, thank you.
Hello, if there is somebody who needs some references for their presentations on Saturday, please email us. See you tomorrow.